So we have generated the reciprocal functions using our chordic algorithm. But our reciprocal functions are going to only operate over, again, plus and minus pi by 2. But we want to extend the domain to any value. That is, we want to be able to put in any value into the reciprocal functions and get the correct value out. So if we start off by looking at what the reciprocal of the sine function looks like. So the reciprocal of the sine, we can actually write it as CSCX in the graphical calculator called Desmos. And you can see this is what we're looking at here. Now, if we were to look at this in effect from minus 2 pi, which is here, to plus 2 pi, which is here, you can see that we're going to get a repetition. Okay, so there's going to be some symmetry within this function in the same way that there's symmetry within the sine function. So what we can do is we can actually take the entire domain and we could put the entire domain in the region just from 0 to 2 pi. So we can see that there's going to be a repetition of the function from here to here, and then it repeats again and again, and the same in the negative axis. So if we take all of what is down here, okay, so all of the negative values and all of the positive values greater than 2 pi, and we map them into this region 0 to 2 pi, then that's going to be a start. Now, if they're in the region 0 to 2 pi, we can then separate the regions into our 4 quadrants. So we would have one quadrant which would be this section here, and then the second quadrant would be this section, and then we would have a third quadrant which would be this section here, and finally our fourth quadrant which would be this section. So you can see here that the actual shape here in the first quadrant is actually repeated, and it's repeated in this quadrant here, and it's simply this part reflected in this line here. Okay, so as if we reflect this over, we get this part of the graph. And the same here, if we take this whole section here and we reflect it in the x-axis, again we can reflect it over, and all of the other 3 quadrants in effect can be reflected over into the quadrant 0 to pi by 2. Now, we've seen that previously when we looked at extending the sine function over the entire domain. So we don't want to get into too much mathematical detail because we have worked through a full example of this before in a previous course when we looked at extending the range for the sine and the cosine functions and also the tan function whenever we were using fixed point numbers and we were using the Taylor series approximations. But let's have a little look at just a little bit of the mathematics just to show that it's there and you can have a look and see exactly how it works. And then we will go on, we'll have a look at the code and we'll see it actually working. So the reciprocal sine function is called the cosecant function. So the goal then is to have the cosecant function, which is 1 upon the value of sine x, and it's for any real value of x. And we're going to use it by first of all noting that the chordic algorithm is going to be accurate over minus pi by 2 to pi by 2. So the chordic algorithm will allow us to actually have this accuracy, but we're only really needing to have the accuracy over 0 to pi by 2. So we're going to take the 0 to pi by 2, and this is going to give us our reference angle alpha. So we're going to take whatever angle that we put in, the angle x, and we're going to reference it to an angle which we call alpha, which is within the first quadrant. That is 0 to pi by 2. So that's just a fancy way of saying we're going to fold all of the angles into 0 to pi by 2. And we're going to not only do that, we're going to have to deal with the signs. So we're going to have to change the sign of the angles depending on which quadrant the angles are in. And we've seen that when we looked at the figure in Desmos, because we're going to have to reflect in the x-axis or reflect in the y-axis or in both of them. So we're going to have to change the sign of the initial angles from positive to negative in some instances. So in the end, what we're going to end up with is we're going to take our original input x, and it's going to be generated by the multiplication of a sine and also the folding of this into the reference angle alpha. So now the step one that we got here is the periodicity. So we're going to wrap in basically one turn. Okay, so we're going to take everything that's out with the 0 to 2 pi, and we're going to fold it into the actual 0 to 2 pi. So mathematically speaking, what you're doing is you're looking at x, and it's going to be modulo 2 pi. So here are the criteria for actually doing the folding. Now I'm not going to go through every single one of them here. As I said before, we've seen something similar when we looked at the sine function for folding, and this is the similar set of equations but for the reciprocal of the sine. So we can see here that what we do is dependent on which quadrant we're in. If we're already in quadrant 1, then nothing's going to happen to the sine, and the value for our angle alpha is just the original angle we started with. We don't really need to do anything. Well, we don't do anything. Now if it's in quadrant 2, we do pi minus that initial angle alpha. It's pi minus, the angle x to give us the angle alpha, the reference angle. And if it's in the quadrant 3, we're going to be our x minus pi, and if it's quadrant 4, it's 2 pi minus x. And you can see the sign changes here. So we're going to have to build the algorithm that does this folding after we have shifted down to the angles from 0 to 2 pi. So this in effect is the second stage. The first stage is get everything into 0 to 2 pi, and the second stage is shift the 3 quadrants into the single quadrant, which is the 0 to pi by 2. So the final step we're going to look at is what we've termed here pole awareness. Okay, so in engineering terms, we talk about the idea of a pole, but really what we're talking about mathematically is an asymptote. So this is where the value doesn't exist at a particular point. So if we go left of the point, the value will go off to say plus or minus infinity. If we go right to the point of the point, the value will go off to plus and minus infinity. So it won't actually exist at the point. Now, if we fold all of the values into the 0 to pi by 2, then the point where this asymptote appears is going to be at the point 0. So really what we're saying is that the absolute value of this cosecant function is going to tend off to infinity. So this will be plus infinity, as the angle tends towards 0 from the positive side. So all we're really saying is, as the angle tends towards 0, so if it becomes, let's say in radians, it becomes 0.5 radians, 0.3, 0.2, 0.001, 0.00001. As it gets smaller and smaller from the positive side, then the value for our cosecant is going to head off towards plus infinity. So what we want to do then is really, in practice, what we want to do is treat the value alpha as being less than or equal to some define value epsilon. Okay, so this epsilon value is going to be in effect defined by our floating point numbers. So we've got a 16-bit floating point number. So we're wanting to find the smallest value of alpha, which is going to give us the largest value of the floating point output. Okay, so we're just really having a check just to find out where the what the smallest value is that we can put in that will give us a meaningful output within the full range of our 16-bit floating point numbers. Okay, so the final little bit of mathematics, if we put it down in a mathematical sense, is that we're going to have the cosec x function is going to have the sine. It's also going to have the cosecant of our reference angle alpha. So this has all been folded and it's all, the signs have all changed, and it's now in the range where alpha is in the value 0 to pi by 2, and the value for our s is going to be plus and minus 1. So I've defined what we're doing here a bit more mathematically rigorously than we did whenever we looked at the same sort of thing for the folding of the sine function. But it's quite a neat and tidy way of describing exactly what it is we're doing. So let's go ahead and we'll have a little look at the code, and we'll see where the code is placed, and then we'll see it actually working. So if we drop into the Visual Studio Code Editor in RTM16 in the ASM folder, we can go into the floating point library, so floating point lib.asm, and you'll see that I've added 3 other functions in here. So we've got fold underscore the cosec, fold underscore sec, and fold underscore cot. Now there's a C in front of each of them to remind us that we're actually using the chordic algorithm for each of these. So these are the 3 extra folds that we're going to have to use in order to ensure that we can extend the domain of all of our reciprocal functions. So the very first one here is 0 cross 5, 500. So we'll have a wee look and see where that is. So this is it here. Now I'm not going to go through all of the details of this code. It's very similar in nature to the code that we used in order to generate the same folding functions for the sine, the cosine and the tangent. So it's just a very, very similar code. So let's go ahead, and we know where the code is. So let's generate a program, and we will use that program in order to print off the reciprocal sine function onto our screen. So if we go down to another file here, which is called chordic underscore CSC. So CSC stands for cosecant, and it's underscore full, just telling us that we're going to use the full domain as the input. So we're going to use this code here in order to plot off our cosecant function. Now we're just using the same type of code that we've seen previously when we were plotting off our arctan functions and the sine functions and the other trigonometric functions that we've used. So it's a very, very similar piece of code. Now the only difference obviously now is that we're going to now jump to the subroutine cosecant underscore full. That's what I've called it here. And of course that's going to be at this address here, which is the 0 cross 5500. So we're going to get down to this point here, and then we're going to jump to this subroutine, which is going to implement the folding, and then it's going to return the final result, and then we're going to multiply it in order to make it a little bit larger, and then we can plot it off with our graphics underscore fplot. And it works through, it will add on the increments, and it will go back to the beginning of the code here, and it will continue round until it has worked out every single point. So let's actually go, and first of all we will run it in the emulator. So the first thing we will do is assemble the file. And you can see here it's got assembly successful. We'll then go run, emulate file, and this will run up the emulator. We will then type in R for run. So that's it being emulated, and then GD for graphics dump. So we've now got the graphics.dat file. So we can get into our machine and we can go into the RAM and we can open up the splash.mc file in order to plot everything onto the screen. And then we can get into the graphics card and we can clear off whatever existed, and we can go edit, open, and then we can add in our graphics.dat file, which is in the RMT16 root folder. There it is there. Okay, so that's us loaded that in. We can now go ahead and we will run the simulation. So the simulation will take maybe a minute or so in order to render completely on the screen, but you can see the points starting to appear now. So I will fast forward this and I'll get you at the end of the simulation. So that's us generated our reciprocal sine function from -2 pi to +2 pi using our emulator. Now let's go ahead and we'll have a look and we'll see what it actually looks like whenever we render it directly from our machine. So we will load the actual code into the machine. So we go to our RAM, edit contents, open. Now the file we're going to look for is our cordec underscore, and we've called it csc underscore full.mc. So this one here. And then we can get in and we can simulate it. Now this is going to take a lot longer to run. So what I'll do is I will just go to the end of the program and I'll show you what the final outcome looks like. So that's it, nearly finished rendering on the actual machine, and you can see we've got from -2 pi to +2 pi, we've got our reciprocal sine function. Now just to show you that it is actually doing something, we can drop into the CPU and we can have a look at we can see everything working away. So these are all the sets and enables, all functioning and all being controlled by our micro-coded ROM. So now we're able to generate the arc sine function. In the next two videos we'll look at the the reciprocal sine function, and in the next two videos we will go ahead and look at the reciprocal cosine and the reciprocal tangent. So thank you for listening. I'll get you on the next video. Goodbye.